All right, so welcome to lecture 13 here. And last class we talked about kinematics or manipulators. I want to Jack reminded me of some things I didn't share. So I was like, oh, I might should just talk about that. So I changed the notes today a little bit, include a bit more material on that. And therefore I'm a lecture behind, but I may stop here this lecture or may have a lecture on Thursday. But I'm leaning to having a laboratory on Thursday using the UR systems, and also the ABB and also the FANUC. And I don't know if I can cram that in one day, so that may come into 2 days, depending on how it's going. We have limited computing stuff too, so we had to probably break it up in different larger groups and things to get that. So it might not be a formal write up. It just kind of everybody get a chance to actually maybe write some code and just kind of show you how things work. And if I got some things in Servo Vision that I was trying to get to today, but I'm going to preview that today, and I just may show off that as well. So we're just going to use robot system to actually do some audio detection and then grapsing. And so and that's going to lead into a homework 3 that I did post today. I don't know if you looked at your and I will let you use groups for that one because it is going to be a server vision. You'll be using Python to solve that. And so you could submit anything in the turn it in or whatever. So you can just put your group names, whatever, in there when you submit that. And I have a due date, I think, in a week or so. I think in a week and a half or something. There's a Friday at some point there. And I'm not going to talk about that today as I go through some of these examples. So last class we talked about kinematics, forward and inverse. I showed one method doing that, and that's called a link chain method. To me, that is the easier method to explain that. But there is a one that's currently used mostly now is this URDF. I'll show you why. And where things started was back in the days of DH, and that's one of the more complex ones. But I will show you that so you have exposure to that. And then that they have a modified DH and original DH. And I used original, and some professors use the modified, and so it's slightly different configuration, but it all kind of works together. But at the end of the day, that 4x4 matrix is going to rotation, translation component, and they're going to be identical depending on whatever method you do. It's going to be the same answer. There are some pros and cons in each one of these methods. The link chain is easier to kind of visualize and see. You're just doing rotations and translations. The URDF will give you the capability to add CAD meshes in there. You can add some friction coefficients. You got mass. You got color. And you can have a more of a visual effect that you can't do in some of the other systems. And the DH would also and you also could put joint limits. A lot of robot systems can't do 360 degrees. They have a limited motion. So you could put those min and max joints in that systems, and you compute a solution for those min and max. And a DH is more like a script you can read in your DH table, which is your A matrix for that in-degree freedom robot. And it allows a way to having the same code base, you just upload your DH for that particular robot and be able to get the configuration for that as well. And then I want to combine everything together, and that's be servo vision. So be able to detect an object, see the location, pose an object, and now I want to grab this object. So I want to figure out what it is, and then make my end effector equal to the object, and then therefore your object, and then you have to back compute the angles to make the robot move. And I wanted to show you a 3D example of that. And I'll probably show that when we do the labs on Thursday there. And that's kind of wrapping up the material at that point there. So I'm going to start off with a review. This is what we covered last time. And we only using Revolute and prismatic joints there. And they are spherical ball motion joints that are available, not very common, but there are some systems that can do that. It's very hard to manufacture a ball joint versus a rotation. And which we're going to use an R for that, and prismatic means you'll be able to translate there. And you have a combination of R's and P's, so rotation and prismatic, to make up a robot system. And these are some of the basic configuration. PPP is prismatic, SYZ, and then you have a rotation prismatic. And you could combine these different configurations to have a 6-degree or n-degree freedom system. But these are the basics here. And once you have this combination down, you can be as creative as you want to have an n-degree freedom system. But all of this is going to be a 4x4 matrix, and which we're going to call the homogeneous solution or the transformation matrix of that particular robotic system. I didn't talk about this here as well. Might as well bring this up here. All robots or have some kind of interfactor. I call it a gripper or whatever the tool is. And it has also an orientation too. So it's a tool frame and a base frame. And this N normal, this A stands for approach. And then this would be like the 90 degrees from there. So I usually approach an object in the A direction. It's usually the Z direction. And that's where the robot, the Z-axis is usually for a robot gripper. So if you look at the UR, the Z-axis for the tool frame is aligned with the gripper. The Z-axis for the base frame and the robot is pointing up in the air. And then the Z-axis is where I want to do that moment there. So even when I'm doing a rotation joint, this is usually my Z-axis in most robotic systems, because that's the axis that allows the degree of freedom to happen. And so that's where the Z-axis is the most important, and the X is the second, and the Y, we kind of just whatever it happens. And it's prismatic, I'm going up and down, so my Z will either be going up in the air or down, and that will allow you motion in that direction there. So you could have, it could be inverted as well, and it still meets the criteria. And this could be going in the page, out of the page, and it's still going to resolve that. So if I want to approach an object to pick it up, if I know the XYZ location of the object, but I also want to know the orientation of the A vector, so I can approach it this way, or I can approach it this way, I can approach it whatever direction you need to do to grasp the object there. And so that this is also important for grasping or any kind of manipulation, is the tool frame itself. So we're going to be using at least the UR and the FANUC system, and then if we have time, I'm also going to bring in the ABB, which works very similar to the UR. The UR is my preferred one for getting started. It also it's easier to interact with, like some software interface as well. So there's a lot of Python interaction with it as well, or you can program it on there. And the programs is more block. You can just kind of drag something on there and click and go. And the FANUC is a more of an industrial system, and it has its own COBOL language there. It's more like C-like, and it has more of a rich programming language. But it all have some kind of teaching pendant that allows you to kind of jog the system around. And this is what it looks like here. You could jog in joint coordinates to base. This is a 6-degree freedom. So base, shoulder, elbow, and the 3 axes of the wrist. Or you can move it in the tool frame, which would be the Cartesian movement. And there's a trajectory between these two. And this would be the inverse kinematics. This is going to compute the going from the tool frame to the joint frame is the kinematics of the system there. And there's a lot of libraries that solve for that already. And I'm going to show you we showed you how to do that during the chain method, but I'm going to show you some more examples of that too today using some other methods. And so the forward kinematics is, where is the end effector? How do you determine that given the joints? And then the LOA is back to be the inverse kinematics here. And this is a better drawing of that system here. Where is your tool frame? Is where it's important. Where the object want to pick up is important. And you may want to know where the frames of the whole system is. And that's for collision avoidance. So if you want to be able, you want to know what your end effector is, if I'm picking up here, but I also want to know what these links are. And so I'm not trying to pick up an object through this table here. I might have to go around and pick up the object here. And so we do some more obstacle avoidance. And that's built into most common libraries now. We'll be able to look at the entire workspace and do collision avoidance. And that's another advantage of using this URDF. It has a collision matrix as well. You could describe everything with boxes, and then it's going to check for collisions before you do that movement. And you can see if you could collide into an object before, because you have multiple solutions to an object as well. So you could find a solution that doesn't involve any collision. And everything becomes a 4x4 matrix, homogeneous matrix with your rotation component. And you can see here the N, O, and A. So this is N is corresponding to the X-axis. If you do a vector in the X direction, the O is your Y vector, and your approach, again, this is the Z. So I'm approaching an object in my Z direction, but a 3x3 matrix can stand for row, pitch, and yaw, or a quaternion, or any other Euler. And this is going to be your location, the X location, the Y location, and the Z location. And this is always going to be a 1 to make it a square matrix. And so you have we would have had a 4x3, and you want a 4x4 because you wanted to invert this matrix, so we had to make it a 1. There are situations, not in robotics, but in computer graphics, where this could change from a different number from 1 here. And they do that for scaling an object. So you want to make an object smaller, bigger. This is almost your scale factor here. So this is a scale factor of 1. So that's the real size of the object. And so in computer vision, if you want to zoom in on the mouse and still be at that same location, you could change the scale factor to 1 to whatever you zoom in there. And that's how they do that. If you play in a video game, if you zoom in on there, you can get the XYZ location of that object there and then render that. But since in robotics and automation, the size of the object as it fits, hopefully it's not going to expand or contract. Well, it could be, but not. We're assuming that the object fits, and so we always use a 1 here, and this we put zeros here to do that. And so this is a 3 degree of freedom. This will usually be Q1, Q2, and Q3. Where here this is theta 1, theta 2. So we're assuming this is rotation and rotation, rotation. So a 3R robot, and it has a 4x4 matrix here. And we're assuming this is a 6 degree freedom robot, all R's, so all rotation joints. Or this would be a Q, prismatic joints here, and this is still a 4x4 matrix. And you're doing the chain rule, we just do the transformation with all the things inside of that and have a single transformation. And the inverse is just going backwards. And we showed this method here. If we're doing, this is a 2 degree freedom, it rotates. With just 1 degree of freedom, it just rotates. So that's a rotation followed by translation. And we do this is the pose graph that we talked about. So that is just the dot product of this. And here is your from end effect, the base to the end effector. End effector we can call E, 0 we call the base or the origin. And for here, 2 degree freedoms, I want to rotate, then translate. I'm on the red link. And then I want to get on the blue link. I want to rotate and then translate. And that chain is the same thing as the origin to the end effector here. And this one here is a rotation prismatic. So this is the RP example. We have rotation and prismatic link. And I have a rotation component and a translation component. And I've done the pose to that. So doing the kinematic chain, you could do, so there's a rotation, translation, rotation, translation. And I did the math there. I get a matrix representing the XY location and the orientation of that. And this is a 2D example, so it's a 3x3, and a 3D example will be a 4x4 matrix. And I showed some Python code to do these, and this is what you're going to be using to assist with your last homework. Given the robot system, you need to compute that A matrix or that T matrix in this case here, and then you need to extract the location of your part and the orientation of that part. And you can utilize these scripts to help you write the code here. You have to add some more stuff to your code there to make it for the correct robot. And there is a tool for Teach to allow you to visualize that, and you can be able to actually move your joints here, and you can see the location. And your roll pitch yaw here is the there. And you can certain systems do use quaternion, so you have to convert the roll pitch and yaw to a Q vector, depending on your system. And some of these are in radians and some of these are in degrees. By default, this is in radians for this, and you can use the math.degrees to go back and forth. And this is the inverse. This is one method to do the inverse. Again, there's multiple ways to do the inverse. I have this T matrix here, and so I can just invert this T matrix, and I can also do the inverse kinematics, and then back compute your orientation and PX, PY, PZ. That doesn't always work. And so this method here is doing a optimization, and this may not always work either, but it may give you a solution that gets you close to there. You may not converge to exactly with the error going down to 0, 0. And you may not find the answer. You may try to pick an object that's too far away, and you're just not going to be able to compute the solution. So it may not be a valid solution for inverse kinematics. And there will be probably a valid solution for forward kinematics, but not for the inverse kinematics. And so we approximate that solution, and then traditionally this would be in some kind of closed loop system, and so you would get there, and then you would just do a feedback loop, and you would just keep iterating this and getting closer and closer to your solution to get, and that's usually how it's done in programming. So that was the method we talked about. The other one is the more common for the newer systems. They're using this URDF. And this one is an example here from Wiki here, but you just, in a XML format, you just describe your robot system here, and it gives you a good way. So this is a joint 1. So this is a 2-degree freedom robot. We got an R here and an R here. The origin of that is at this Z location. And this one has a little Y offset here. And I'm going to link these two together, so the parent and child, and that gives you, then we could just import this into our system and start using that. And for example, we're using the UR systems. And here is I think it's this one here. Nope. And this one's actually for the ROS 2, but you'll be able to see I could put more information here. Here's my geometry for the base here. I could put a collision matrix, which is going to be great. Now I could do collision detection of that option here. And I could put inertia matrix there. I could put mass in here. And then below here is where I do my base link here, and I could add a lot more information here to the system. And this is why this is more rich than using some of the other systems here. And so this also has the mesh files, and so you could visualize here. These are the CAD files for the different things here. So you could actually have a 3D visual tool of that there, and then that's the power of using the URDF format. And that seems to be the latest trend in the robotics, is using this format here. And so I have some Python code here that just happens to show you by loading in this URDF. You can just load in the file, and I'm just going to show you some of that. And so this code here, I'm going to import this, and I'm just going to load the URDF of the UR5 robot. And here it gives me a lot of information about the so I put in like a little happy Halloween here, but you can see the UR5 is a 6-degree freedom system. Our rotation, it has no prismatic links. It has one gripper, and this is my links here. And starting the whirl is the whirl frame, the origin, and then the base link. And then you go the shoulder, the upper. You go all the way, making your way to the end effector, which is at the wrist. And there is a tool as well. And you can see the offsets here. And so also print it, if you want to know where the gripper is located, given a certain arrangement, you could just print that out. And I'm located at, this is my T matrix here, which is that 4x4 matrix, and I could extract the XYZ from there. And I'm also could do things that I couldn't do, such as dynamics. And so when everything has mass, so when you, even in motion, If you try to move something really heavy at a high velocity into a corner, a turn or something, using that momentum is going to give you some error in your position there. So you want to put in the mass. So this is in kilograms. So the base of that robot is 4 kilograms approximately, and then and that's the heaviest part. Well, actually, the arm is heavier, but the base is usually heavy to keep it from stable. And then you just work it all the ways up to the thing. And here's the inertia matrix of that system, the diagonal there. And or if you wanted to learn more about this, we could talk later on offline about that. And I could give you more information about that there. So dynamics and control system is something that would be taught in a mechanical engineer if you want to learn more about that for the robotic side of things. And also, if you want to do torque control as well on the joints and things, we could talk about that at another time. But that it has the ability to do all of that with this built-in GURDF system there. And so there's just some readouts here, and here's the dynamics here. Another method, and this is one of the original methods, is just was it dynamic Haverberg? Is two last guys' names they merged together and came up with this. I just call it a DH. This is like 1960 time period, 65. This is right when the Puma came out, and they want to go from one location to the other location, and so it's going to be you can get any pose to another pose within 4 transformations. And so I could, even if this is a drone, if I want to go from one location to another location, I could get there in 4 or less steps. If you want to talk about rotations and translation rotation. And so they make every single, like, this is the links here. If I want to go from this link to this link here, I could go through a series of rotations, translations, and rotation translations. And they're going to extract these components such as the D, the height offsets, the A is going to be the distance between the x-axis, the rotation in the z-axis is going to be this alpha term, and this theta term is going to be the rotation about z. And they're going to link these matrices together to return still a single 4x4 matrix here. And these are some of the definitions coming from their definition. And so the alpha is the twisting in the z, and then your theta is the joint between your z-axis here. That's still going to be this rotation in Z by this translation in Z by this translation in X and this rotation in X. And those are still 4x4 matrix. So this is the rotation matrix of the Z. This is a translation. So there's no rotation. That's identity matrix here. And then you have your transformation on the Z. So this is X, Y, and Z. And this is your translation in the A axis is the X. And then here's your rotation matrix here. So what is a 4x4 times a 4x4 dot product of 4x4 by a 4x4? It's still going to be equal to a 4x4, which they call the A matrix. And this is this is a generic solution for going from any pose to another pose, but it's done in 4 steps. And you don't necessarily have to go in 4 steps. We know we just did one from rotation and translation, but this is a generic solution here.
Yeah. Is it for all the rotation translation, they only move in one axis? For example, rotation, I think it's only for Z. Is that correct?
Yeah, sure. Your rotation is only about Z. That's correct. And so you only use Z and X axis in the DH convention there. And my other convention, I could use the rotation in Y to get to certain things here. I use it here, but it doesn't matter what and this is the original transformation, and then some books actually use you might see a I -1 and alpha I -1, and so they use a actually different order here, and you have a different A matrix for that, and that's the modified DH table that certain books use. The older book, like Craig Robotics, use that, and certain professors, the older professors still use that kind of method as well. And I used the original one. And you will have it's still a series of 4 movements. It's a different A matrix, but it's still however you get there, you still gonna get to the same spot. But this is a good way to now, if you just have the standard, you could just reading a DH table for that particular robot, and then you'd be able to compute the A matrix. And so you would just program this A matrix into your computer, and you're just gonna read in this table the thetas, the alphas, and you have a system here. And so for example here, this configuration here, this is my 4x4 matrix. This would be my DH table for that. And I could just read in this as a script and then solve the A matrix for that. And then I could do the math from there. And here is another popular one. You may have seen this one here. This is the Fennec. And I've worked out the DH table for it. This also has some joint limits here. So the first joint could go 360 degrees. So I mean, it could move all the way around, but that is the base. The other joint only has 230-degree motion here. And I can't remember why this has for higher than that. And you can only move at certain speeds too. So this is the actual for that particular robot. And this is stand for the short arm version. There is a 200 IDF with by 4 without that, and then they do have other different product lines as well. But we have 2 of these. You've probably seen in the lab itself. Going through the same kind of thing here. This is the DH table for that particular robot. If you want to figure out why the teaching pin is giving you these XYs, these forward and inverse kinematics, this is what you could use, and you could do some simulation if you want to do that of the actual Fennec system. And the Fennec also have simulators too, so you don't have to necessarily model your own. And most robot system has simulators as well. So today I wanted to talk about this system here. This is also in Fitzwiller 2200. And this is relating to your homework. So I have a robotic system here, a manipulator, and this is the UR5E. It has a gripper, and it has a Z camera. You can see by the bullet 2 here. I want to detect the location of this object 3, and I want to grasp that object 3. So how can you determine the location of this object 3 with respect to the base? That's the question. And that's what the homework assignment is going to walk you through here. So I have a UR. Oh, this is origin. This is my UR5 base there. I got that has some links here. And now we know this is a rotation link, this is a rotation link, this is a rotation link, rotation. And so this is a 6R system. Sometimes I just say 6R. And so they has some joints here, meaning there will be some joints to get me to my location. This is my end effector. And we could connect these here. And there could be some tool there. And so that is my gripper, which I'm calling 5 here. And it has a camera attached to the robot. And it's really is this direction. This is some kind of offset here, and it could be a rotation too. Let's say this is my z-axis now, and I detected the object. It's probably at the same height. Let's see. I'm gonna call this object 8 here. And I'm going to use this is the Z camera, which does it has an RGB, it's a stereo vision system. So it has 2 RGB, and they compute a point cloud, which you can call it PCL, which gives you X, Y, Z coordinates here. So this is a blob here, and all you'll be able to, you can cluster these together and find a center to find the center of the object there. But we're just going to look at, we want to detect this is a box here. I just want to detect the edge of that box here. And that's where we're going to pick it up at. That may not be where you really want to pick it up there. So the camera is here, detects this guy here. And we physically mount that camera on the robot. So there's a fixed mount. So we know the length there. Remember, the solid is known and the dotted is unknown. And so I'm looking for this object with respect to the base. So that is an unknown to me. And that's going to be called the origin to DH there. And so what is that transformation? Yes, you could do the chain method here, but we know, assuming we know we just already know this location here. So we do know this already. This is the same thing as the forward kinematics. Given theta 1, Q1, Q2, Q3, Q4, Q5, and Q6. So given my Q's 1 through 0 to 6, or given 1 to 6 here. In this case, it's the same thing as theta 1 to theta 6, because they're all rotation judged. I can compute my X, Y, Z, roll, pitch, and yaw of my robot system using the forward kinematics. And that's going to be equal to the origin to the end effector. I'm going to call that E here. So this here is OLE here. This is my end effector to my camera system. And this is my camera to my object. And now I want to know my object to my origin to the object. So how do I find this?
It will be base
to the end effector. And I will go ahead, I'll just make it go back a step here. That is going in the positive direction. So I'm here now.
In effect with the camera.
Yeah. Effect camera, still positive. And then camera to the object age. And since they are positive, this is gonna just become a dot product there. And then you're left with a 4x4 matrix with your rotation component and then your pH as Y and Z the one of your location there. So now I know where this object is with the respect of my, and so if I want to graph this here, how can I do that? So this is my grippers here. So I want to set that equal to, or approximately equal to, the origin of the H here, right? So if I set my end effector equal to my object, then I'm at the same location. I said approximately equal to because I may have X, Y, and Z. I may want to pick it up. If I want to pick it up from the top here, or I may want to pick it up from the side. I have a little bit of control of how the orientation I pick it up. And so if I set those two equal to each other, and then I do the inverse kinematics, I will get back my Q1, Q2, Q3, Q4, Q5, and Q6. And if I program my original Q values, this is my goal, and this would be my current location. This is something called Q01 or Q0 or something. This is where I'm currently at. My delta Q, my change in Q, is how much I need. So I'm going from 0 degrees to 30 degrees will be how I would program to actually get my robot to the system. So my delta, computing the delta Qs, And then I could do a closed loop system on my delta, each one of the joints there, and the robot would move to that location. And then I could just activate the gripper. And so we have all the information we need now to do like a servo vision program here. So if I want to, the only thing I'm missing really is this camera. I'm assuming that my camera can see this object here. So I follow the camera that does this and automatically sends this out here. Or we'll have to do some RGB camera and do some open CV or something to actually do this here. But I'm assuming not getting this output out there. And the other way around, if I knew what the object is and I want to figure out the way, I guess you not necessarily need to find some. You can find any missing thing by just going through the chain there of the system here. All right.
So when you try to move the arm to our position, we first need to calculate the forward kinematic and then do backward kinematic to figure out the angle.
Yep. So you're doing the forward and the inverse kinematics. And so you can use the DH approach there. You can use the kinematic chain. You can use or whatever to get that, but you need to do the forward and inverse. You did to solve the complete problem. And so our controller usually does the math for you. If it's a nicer system, it would be like the UR series. But if you have your own, if you're just building your own robot system with some servo motors and things like that, your microcontroller, you could do this math. You could stick it a far forward, and it would still be able to run that dot product, or whatever. Especially if you use the other technique here, I could solve for this and like using it, even like a Raspberry Pi. If I hard code that in, I just still do cosines and sines, and I could still, so I don't have to actually do the dot product, but I can still do a cosine times the theta, a sine times the theta, and compute that. If I'm interested in the SYZ position, it'll be the A1 times that cosine of the angle, and I can still do that. And A1 would be a length, a fixed length in your system. So that is one of the advantages of this here, is far as the computing power is less to do that. And so that will give you the ability to pick up an object or do something with the object and that you're trying to do here. Yep.
From the last slide, is A represent each joint transformation, and then you just.
And then you would dot product all the way, so it'd still be one A at the end with the combination of. So if this was a 3-degree freedom robots, you would have 3 A's, and then you have A, and the total A would be A1 dot product by A2 times A2.
So if you have 7 joint, you would be A1 times A2 to A7.
Yep. And so it would, and symbolically it will look really long, but that's what you want to throw the numbers really fast and then do it. Yep.
That's for transformation. How about rotation?
Yep. So you still have your rotation is just 3x3 component out of here. And so you would need to extract your row pitch and yaw from this guy here.
So then the rest of the distance will be the same.
What was that?
So if we do a rotation, only the 3x3 would be changing, is that correct?
Yep. If you just per rotation with no translation, and there's only 3x3 we're changing here.
Okay.
Yeah, so you could back compute your rotations. It gets a little complex, but that's why the that solver helps you out doing that as well. And there's another algorithm called A10-2 if you're interested in that. It will help you back compute some of these angles. So that is the bigger picture. So I was trying to do a demonstration of this and I didn't quite get it working. And I couldn't get the login and stuff work. But this is a robot system here. I took a picture of the pan today. I don't know if you can see it. So this is my real numbers. So the robot gripper is at this this XY position, roll, pitch, and yaw. And you would, that roll, pitch, and yaw, just remember the rotation. Roll, pitch, and yaw is actually the rotation in Z times the rotation on Y times the rotation in X. And that will be a 3x3 component. And then you have your X, Y, and Z scale factor. And that will give you a 4x4 matrix there. And of that, and this would be of your, this is equal to the end effector. And so my end effector is located as this SYZ here. And this is my kinematic. So to get to there, that Q1 variable is 94 degrees. And so on here to get me to that location there. So I fired the Z camera up. Let me just change my slots here so you could. And this is kind of the output of, this is, I also had the RGB image here, and it's also had a depth map. But this is what the point cloud looks like from the Z camera. They are a better system. This is the older Z2. But each one of these points is an XYZ position there. And so I could use other algorithms, segmentation here. This is a box that I put on the conveyor system. You can see it from the top down. This is like a tissue box, and these are just those two 3D printed parts. And I'm trying to determine the location in 3D of these things here, so I can actually maybe grab that here. But you can see here, I mean, there is a point here. I can physically measure that point and get this XYZ coordinate here. So I know my XYZ of this here. And I can pick it up. If I want to pick it up from the top, then I know that my rotation is, I want to have my A matrix this way. So I know my rotation component. Remember, this is the N O A. So if I want to go, so this is going to be XY, my A matrix is going to be going down here. And I know this would be wherever I detected my X location lines. So I know what my 3x3 that's going to look like here, if I'm going to grasp it from the top down. This may be all once. No, I think it was right. That's right. This is a per Z rotation. I put an A here. This here and here is not right. And so we'll be able to then do the full loop and maybe go and pick up this here. So I may get this working before Thursday and show that. So for the homework, similar problem. I just simplified it a little bit. Instead of using this UR series, we're using this robot here, and I got rid of 1 degree of freedom. So it's just a 3R system. And I want to do the same thing. Here are my robots on the 3 Qs here. I have a camera located on the robot, and it finds an object, and I want to figure out what the object is, and then I want to go grab it with the robot. And so and then I ask you to go through these questions here. So this is the chain rule for that, or you can use a different method here. I'm giving you all the links to the robot are equal to 1 unit for this particular system. So your A's is the length of it's gonna be 1. And I just want to know what these joint variables Q1, Q2, and Q3. So really theta 1, theta 2, and theta 3, is 3 rotation joints are. And I go through a series of questions to help you kind of get to the final answer. And that is homework 3 there, which is already posted there. And then you can use groups, you can use some Python, we can do whatever you want to, they come with that. So you're doing this problem here with a different robot system. So any questions on that? Right, so there is and this is moving into next class. We're going to actually go into fits with the 2200, and we're going to actually start moving. There are some simulators available if you want to simulate the UR5 simulator. They are in Linux, so you either do a virtual machine or a Docker container, or we have your Linux environment set up. You'd be able to, and it does use the Java runtime thing too as well. We'll show that in the next class. So the schedule is we're going to probably on next class, I will at least do the UR and the FANUC, the two most popular, may get to the ABB, depends on how it goes there. And that will wrap up the course material from there. We still have that homework set, the homework 3, and I still like to have some project descriptions too. So and then I'm going to kind of turn you loose on the lab. There will be another class using the lab towards the end that same time period too. So I think I'll be using the PLCs. So we just got to be considerate of some sharing that resources there. And then we'll have our exam on the 21st. We could do a review session if you want to do that. I would just send me an email and we could set up something between that. There won't be any more physical class. I'll be in the labs or whatever. You could just come by, or you can arrange with your own team about however you want to tackle that there. Yep.
Oh, I was gonna say, would the review session be like a class?
I could do, we'll come back here on Tuesday and Thursday before then and do I can't remember what date this is on. I think is it a Thursday? I think this is right before Halloween, Thanksgiving.
Cause I was gonna say, maybe we would just take the class work now and see if we want to do it.
So that is that Tuesday before, so we can do, if you want to do a review session anytime, I guess anytime after that, really. But I will give you some time to do the homework. And then so that was it the 14th or the 16th, we could do review session. Yeah. Doing the same class time period.
Yeah, I think I'd be interested in that. I
You
was
want-
gonna say if we went to
So we just
class.
want to do the 16th, what day works? 16th. Okay, we do a and this is the exam is cumulative, so it covers all the topics. It will not, it'll be just designed for an hour, whatever, so it won't be going in. A lot of the lab stuff, we probably won't, you're not gonna program the PLC or something in for the exam. But
And then there's nothing during like exam week.
and then the exam week, that day of the official exam is when the projects demonstrations are due by. And if you want to do it earlier than that, that's fine, but that'd be the last date you could demonstrate that.
Do you know that date?
I meant to look it up, I don't.
In the exam, I guess it's basically just gonna be the homework. content.
Yep, yeah. Yeah, as you said, I meant to look it up, I don't remember. Whatever that official scheduled time is, I'll be there to do those. And you could, if you go to the YouTube, you get some ideas from what people did last year. But it just do like a brief and then return everything in by that day period. And last year we did have groups that did it before then. They just gave me an email and say, hey, we're all available at this time. And I just came down and did it. I will still be around pretty much every day. So
Is there a team size like?
no, I'm not gonna do any limitations. We had a group of 1 last year. And then we had a group of 5. So it was all different things. So as long as everyone participated in that team. And for the demos, everybody on the team should be present for that. Yep. Well, I will upload this